You know, some rules in physics seem absolutely set in stone. They're in every textbook, they're what every student learns. But what happens when a team of researchers decides to poke at one of those forbidden rules, and they find something that just shouldn't be there? Well, that's what we're diving into today, the story of how they did it and what it could mean for all of us. So here's the rule they wanted to break. It's all about symmetry. In a gas, all the atoms and molecules are just randomly jumbled up, pointing in every which way. This creates what physicists call a centrosymmetric medium. And because of that perfect, random symmetry, certain things are supposed to be impossible. Like, you can't just take two beams of light, mix them together, and get a third beam whose energy is the sum of the first two. The physics says that the symmetry of the gas will just cancel the whole effect out. It shouldn't happen, period. And that's the question that really drives science forward, isn't it? A team of researchers from the University of Minnesota and Argon National Laboratory looked at that textbook rule and said, let's check. They decided to put this fundamental idea to the test to see if they could actually create this so-called forbidden signal in a real lab. Okay, so if you're going to challenge a textbook, you need a pretty slick experiment. The goal was actually simple on paper, but incredibly tricky to pull off. Basically, fire two super powerful lasers into a chamber full of gas, and then look very, very carefully to see if a new combined light beam comes out the other side. Now, this diagram looks pretty complex, I know, but it really shows you what a challenge this was. Over on the left, you've got this powerful laser creating two different beams of light. They're bounced through all these mirrors and lenses to get their timing and polarization perfectly lined up. Then they're focused down to a tiny point inside that gas chamber in the middle, and finally, all the way on the right, there's a detector, waiting to see if that one impossible signal actually shows up. Let's just break it down into 3 simple steps. First, they fire up 2 different laser beams, one infrared at 1064 nanometers and a green one at 532. Second, they focus both beams into the same tiny spot inside a chamber filled with a simple gas, something like argon or nitrogen. And third, they use this ultra-sensitive detector that's tuned to look for one specific thing, light at exactly 355 nanometers. That's the precise wavelength you'd expect to see if the 2 original photons managed to combine. So they ran the experiment, they fired the lasers, and against everything the textbooks predicted, the detector lit up. They found it, a clear, undeniable, measurable signal at 355 nanometers. They had actually generated the forbidden light. And this graph, this right here, is the proof. It shows the strength of that forbidden signal versus how much gas they pumped into the chamber. And look, for every single gas they tried, helium, nitrogen, oxygen, argon, krypton, it's the same story. The more gas they added, the stronger the signal got. This wasn't some random error or fluke. It was a real, consistent, and repeatable discovery. Of course, in science, you can't just say you found something, you've got to prove it beyond a shadow of a doubt. And this quote from their paper basically says that by carefully measuring exactly how the signal's strength and polarization behaved, they could be 100% certain it was the real deal, the result of that forbidden process. So the technical term for this effect is sum frequency generation, or SFG for short. Think of it kind of like music. If you play 2 different notes on a piano, your ears sometimes hears a third higher tone that's a combination of the 2. In this case, 2 different colors of light mix together to create a brand new, higher energy color of light. It's a process we know about. It just wasn't supposed to be able to happen here. And here is the real kicker. This is the key that unlocks not just the mystery, but the potential of this whole discovery. The signal's intensity didn't just go up with the gas density. It scaled perfectly with the square of the density. This beautiful, precise mathematical relationship, this n-squared dependency, was the final piece of the puzzle. It told them the effect was real, it was predictable, and it was about to become very, very useful. Okay, so finding the signal was just step 1. The next giant hurdle was to figure out why it was there. See, there were some old, pretty obscure theories that suggested this could happen, but only under super specific, weird conditions. The team had to prove that what they found wasn't just some rare exception to an old rule, but something totally new. And this slide lays it out perfectly. The old theory, which involves something called quadrupolar effects, predicted you would only get a signal if your laser beams came in at an angle to each other and had polarizations that were perpendicular. But what did the researchers find? They got a strong signal with beams that were perfectly parallel with the exact same polarization.
The new experiment directly contradicted the old theory's predictions. If you want to see the smoking gun, this graph is it. Just look at the block squares. That's what happened when both of the incoming laser beams were vertically polarized. The signal that came out was also strongly vertically polarized. But according to that old theory, that specific combo should have produced next to nothing. The data just flat out doesn't fit the old explanation.
And just to be extra sure, they tested another idea. They thought, hey, what if our powerful lasers are actually ripping electrons off the gas atoms? That would create a little electric field and break the symmetry. So what they do? They applied a massive external electric field. We're talking 20,000 volts per centimeter, and the signal didn't change one bit. That completely ruled out that explanation, making their discovery even more solid. So a physics rule gets broken, a decades-old mystery is solved. That's cool for physicists, right? But why should the rest of us care? Well, it turns out that by breaking this rule, these researchers accidentally discovered an incredibly powerful new tool for seeing the world around us. This is the real payoff. Remember how the signal strength is tied to the square of the gas density? That means you can use it as a super precise, super fast way to measure that density. And when I say fast, I mean on a picosecond timescale. That's a trillionth of a second. It can work in crazy extreme environments where normal sensors would just melt, like inside the fiery combustion of a jet engine or in a superheated plasma. And maybe the most incredible part? The signal it produces is about 10,000 times stronger than similar techniques, which makes it way more practical to actually use. This is a game changer. You know, a story like this is just a fantastic reminder that even the rules we think are most fundamental are always worth testing. Sometimes they can be broken. It really makes you wonder, right? What other things that we think are totally impossible are just sitting there, waiting for someone to look at them in a new way? This is for entertainment purposes only.